Hello everyone, hope you're all doing great. In this video, I'm going to demystify the chain rule that is used in isoparametric elements. So this video requires you to have some basic understanding, some basic motivation on why we actually use isoparametric elements. And in this particular video, I'm going to demystify the concept of chain rule that is used in isoparametric elements. Of course, conventional mathematicians have given the explanations for this idea of chain rule in the context of isoparametric elements, but I find that explanation to be a little less intuitive. So I just want to get across this concept in an intuitive fashion. So I have got an analogy. You can watch this video and see if it resonates with you. So to begin with, let us consider a mountain with rich flora and fauna that you could see there. And let us say that we have got a person, a field investigator, a naturalist who is interested in this particular project, who wants to measure the temperature at different places in this mountain. So we have our field investigator, Mr. Jack, who can actually measure the value of temperature at different places in this particular mountain. Okay. So as he measures the temperature, he collects the data, and what he is actually going to do with those data, he is going to put it inside the computer, and he is going to find out an equation by using some kind of regression algorithm, how the temperature is actually going to vary at different places. Now, for simplification, we will assume this scenario to be two-dimensional. Of course, mountains are going to be three-dimensional. For this particular physical scenario, we will assume that it is two-dimensional. So temperature is going to be a function of x and y. There you could see the set of coordinate axes x and y, and temperature is just going to be a function of x and y. I'm just going to write a simple equation for temperature in terms of x and y, but this is not a general equation, but this is just for an example. I'm just going to write an equation, temperature as a function of x and y. So here we go. So T of x comma y is equal to a naught plus a1x plus a2y plus a3xy. I will stop right there. Of course, this is a general equation that we have got this equation from a regression algorithm. So from data, we have built this equation. So this is not so I want you to understand that this is an empirically substantiated equation. So the values of a0, a1, a2, a3 are known in this context. Okay. So I'm just going to put a tick mark as we assume that the values of a0, a1, a2, a3 are known in this context. Now, since we have this equation for temperature that enables us to tell what is the value of temperature at any point on this mountain, I can just differentiate this equation with respect to x. I can also differentiate this equation for temperature with respect to y. So I'm going to differentiate this temperature equation with respect to x. So we call it as dou t by dou x. And I can also differentiate this equation with respect to y. I will call it as dou t by dou y. And this temperature gradient with respect to x and temperature gradient with respect to y are important for one reason. Suppose that Mr. Jack is going to take from point A to point B along the x direction. And suppose he is traveling a distance of del x along the x direction. So what would be the temperature difference between point A and point B? You can just find it out just by using this temperature gradient. So the temperature difference as Jack goes from the point A to point B along the x direction. Okay, horizontal direction, he is traveling horizontally. So the total change in temperature is given by dou t by dou x into del t. Please keep it in mind that this del t has to be, I'm sorry, this not del t but del x. It's my mistake. So it should be dou t by dou x into del x. So del x is the distance that Mr. Jack is traveling from point A to point B and perfectly along the horizontal direction. Please keep it in mind that this distance Jack is traveling, del x, should be small for this equation, for our computation to hold good. Okay. And similarly, when Mr. Jack is going from point A to point C. Now this time point A to point C is measured along the vertical direction. So in this case, the change in temperature between the point A and point C, this time that is measured in the vertical direction, it is dou T by dou Y into del Y. Okay, so point A to point B, that is Mr. Jack is going from this point A to point B, and that is perfectly along the horizontal direction. This del x is going to be very small for all practical purposes without incurring any serious error in the mathematics. All right, and also Jack is going from the point A to point C. This time Jack is going along the vertical direction, so the distance Jack travels along the vertical direction is del y. So the total change in temperature between point A and point C is given by this equation right here, and the total change in temperature from the point A to point B is given by this equation here. So that's the reason why this gradient, computing this gradient, is going to come in handy. Okay, so we will keep that in our mind. Now what I'm interested in is the contour, the outermost boundaries of this mountain. So let me localize my attention on the outermost boundary of this mountain. So there you could see the violet color, the red color, the orange, the yellow. So these colors are there. That represents the boundary of this mountain. So what I'm going to do is I'm just going to come up with a simple version of the mountain, a two-dimensional mountain. So there you could see the simple version of the mountain. This seems ridiculously simple. So what I mean by a simple version of the mountain that you see here, this is the simple version of the mountain. So this is our actual mountain that is actually looks very complex, and this is a simple mountain. Okay, the simplified version of the mountain that is actually going to enable us to do the calculations in a very simple fashion. Now, why this is simple? In the sense, each and every point on this mountain, on this complex mountain, has a corresponding point on this simple mountain. For example, there is a violet line there, and you could also see the violet line here, which represents the bottom boundary of this mountain. And you could see the yellow line that is representing the left region of the mountain, and you could also see the yellow line that is representing the left region of the simplified mountain. And you could see the orange at the top, and you could also see the orange at the top here. It's a little bit, it's not very visible in an explicit sense, but you could see that there is an orange that is representing the top boundary of the mountain. And you could also see that there is a red, and you could also see the red that is representing the right side of the mountain. But for this simple mountain, of course, the coordinate axes are epsilon and eta. Okay, now this is the relationship between the actual mountain and the simple mountain. Each and every point on the simple mountain has a corresponding point on the actual mountain, and the converse is equally true, right? Each and every point on the actual mountain has a corresponding point on the simple mountain. For example, if there is a point here, and there is a corresponding point on this simple mountain. Okay, likewise, there is a point here, and there is a corresponding point on this simple mountain. Okay, so that is what I mean by each and every point on the actual mountain has a corresponding point on the simple mountain. I hope this concept is clear. Okay, fine. Now, what we are going to do is, let us say that the field investigator, Mr. Jack, is going to take a step from a place called, let us say that a place called Kyle's to a place called Indus. Okay, so these are fictitious places. So I'm just saying that Jack is going to go from the place called Kyle's to the place called Indus, which means that in the hypothetical world, in a simplified world, also Jack is going to travel from a place called Kyle's. Of course, it is a hypothetical simplified version of the world. So I will put a dash there and to a place called Indus. So Jack is going to reach from a place called Kyle's to a place called Indus, and of course this is in a simplified version, so I will just put a dash there. Okay, now if that is the case, now Jack has traveled a distance of say for example del epsilon here. Because Jack is also a field investigator, he is a naturalist, he is a data scientist, so he has got his own machine learning algorithm, and a robust one, and he has got the equations that are built. So Jack also has the equation for t of epsilon comma eta, so he also has this equation. So I'm just simply putting a tick mark, I'm not writing the equation we can assume that Jack has this equation in terms of epsilon and eta. Jack also has the equation for temperature in terms of x and y. So, which means that Jack can actually find the gradient in exactly the same fashion what we did before. So he can find the gradient dou t by dou epsilon, and he can also find the gradient dou t by dou eta. Because Jack is now traveling in this hypothetical world from the place called Kyle's dash to the place called Endel's dash, he can actually find what is the total difference in temperature because he is traveling only along the along the epsilon direction. Del T total is going to be dou T by dou epsilon into del epsilon, whereas del epsilon is the distance Jack has traveled, that is from the place Kyle's dash to the place Endel's dash. Okay, so he's going from Kyle's dash to the place called Endel's dash, and this distance is going to be del epsilon, and that is what is indicated here, just to avoid the confusion. But if you look at this actual world Jack is traveling, so Jack is traveling from the place called Kyle's to the place called Endel's, but you see he has to travel a certain distance along the x direction, and he also has to travel a certain distance along the y direction. To get to the place Endel's, Jack has to travel a certain distance along the x direction, del x, and he also has to travel a certain distance along the y direction, del y. Okay, if that is the case, then we can say the total change in temperature should be the gradient dou t by dou x into del x, the difference in temperature that is happening because Jack has traveled a certain distance del x, and also, right, the Jack has also traveling a certain distance along the y direction, del y. Okay, so that is it. So here I have got two equations. Maybe I can say that I have got two star equations. So this is going to be my star equation number 1, and this is going to be my star equation number 2. I want you to look at these two star equations and how those two star equations come in the first place. The first star equation comes because this first star equation comes from the hypothetical world, the simple world, where Jack is traveling from Kyle's dash to Endel's dash. He has traveled a distance del epsilon. Okay, the second star equation comes because Jack is traveling from Kyle's to Endel's. He has to travel a certain distance del x, and he also is traveling del y to get from Kyle's to Endel's. If that is the case, then the total change in temperature can be given by what is the total change in temperature when Jack is traveling along the x direction, that is del x, and what is the total change in temperature when Jack is traveling along the y direction, that is del y. Okay, so the sum of the two changes in temperature should be the net total change in temperature. Okay, so you could see that in both the cases, as Jack is traveling from Kyle's to Endel's, simultaneously Jack is also, in the hypothetical world, Jack is traveling from Kyle's dash to Endel's dash. So these two worlds are like parallel worlds happening parallelly, simultaneously, spontaneously they are happening. Okay, and as you know, one condition that we have already established, each and every point has a corresponding point on this hypothetical world. So Kyle's has a corresponding place here, Kyle's dash, and Endel's has a corresponding place here. We call it as the Endel's dash. Got it? Very clear. Now, if that is the situation, we can also tell one more situation, that is the total change in temperature. Okay, the values of temperature, the values of the field variable at the place Kyle's, and the value of the field variable at the place Kyle's dash is just going to be the same. This is also a condition that we are forcing, and the value of the field variable at the Endel's and the value of the field variable, which is the temperature at the place Endel's dash, is just going to be the same, which means not only each and every point on this fictitious element has a corresponding point on the actual element, actual world, also the field variable, it may be temperature, or it may be velocity, or it may be displacement. It's just going to be exactly the same on this hypothetical world also. That is also a condition that we are forcing, because this is just our mathematics. We are coming up with the hypothetical world, so we are just forcing the condition. So that is the next point. So first point, each and every point on the actual has a corresponding point on the hypothetical simplified world. Second point, each and every field variable value, magnitude of the field variable at the actual has a corresponding value which is exactly the same as the actual value value. On the hypothetical world also it has the same value. Now if that is the case, then the difference in the field variable, it may be the difference in temperature, or it may be the difference in velocity, or it may be the difference in displacement, then the difference in displacement or the difference in temperature should also be the same. If that is the case, then since the difference in temperature is going to be the same, I can now say, because this is a condition that I am forcing, now I can say that I can equate the first star equation and the second star equation. If that is the case, I can equate the first star equation, which is dou T by dou epsilon into del epsilon, is equal to, I can equate the second star equation with the first star equation, which becomes dou T by dou x into del x plus dou T by dou y into del y. So if that is the case, now what I'm going to do is I'm just going to multiply and divide, I'm just going to multiply by 1 by del epsilon on either side of this equation. Since I'm multiplying by 1 by del epsilon on either side of the equation, I'm not going to do any damage to the equation. If that is the case, I'll be getting dou T by dou epsilon. Because I'm multiplying by 1 by del epsilon, I'll be getting del epsilon in the denominator here. So I'll be getting dou T by dou x into del x divided by, it is del x divided by del epsilon into plus dou T by dou y into del y divided by del epsilon. Okay, so these two are going to go away, and if the value of del x is going to be very, very small, I said that it has to be very small so that we can do the calculations without incurring any serious error in the mathematics. Now I can say that del x is going to become dx, and the del epsilon is just going to become d epsilon. If that is the case, then dou T by dou epsilon is equal to dou T by dou x into dou x divided by dou epsilon plus dou T by dou y into dou y divided by dou epsilon. Okay, so that is it. So this is the equation, the chain rule that I wanted to demystify. Sometimes we may have difficulty in understanding how we actually get this equation. This was the question that I have been asking, how we get this equation. So I think to some extent we can understand how we get this equation with an intuitive example like this. Now, what is the power of this analogy? The power of this analogy is, well, temperature is what Jack is measuring, but Jack can also measure the fluid flow across the hill, right? Jack can also measure the displacement of a particular point on the hill, maybe because of geological actions. So if that is the case, if Jack is going to measure the displacement, then Jack can measure the displacement dou u. So you just simply have to switch the value for temperature in terms of displacement. Let us say that Jack is particularly interested in measuring the displacement along the x direction. Then it will be dou u by dou epsilon is equal to dou T by, this time it's going to be dou u. So it is going to be dou u by dou x into dou x by dou epsilon. All right, so that's my epsilon plus dou u by dou y into dou y by dou epsilon. Of course, this is going to tell you the value of the total change in displacement along the x direction. Suppose Jack is interested in measuring the value of the displacement along the y direction, so that will be dou v by dou epsilon, right? So it can be dou v by dou epsilon is equal to dou v by dou x into dou x by dou epsilon plus dou v by dou y into dou y by dou epsilon. So a little consideration will also tell you that it need not necessarily be just these two equations. You can also say that maybe Jack is taking a little step along the y direction in the hypothetical. Well, in that case, the equation will be dou u by dou eta is going to be equal to dou u by dou x into dou x by dou eta plus dou u by dou y into dou y by dou eta. So Jack can also take a vertical direction, so he can also measure the value of the difference in displacement along the vertical direction when he travels a small neighborhood distance from a place called point A to point C along the vertical direction in the hypothetical world. So if that is the case, that will be dou v by dou eta is equal to dou u by dou I'm sorry, it's dou v by dou eta dou x into dou x by dou eta plus dou v by dou y into dou v by dou eta. You see, just by understanding this particular equation, right, the one that I have shaded in yellow, it is possible for you to write all these equations. Rest of the equations can come in handy. It's very simple, right? Once you've understood the physical meaning of the first equation that I have shaded in yellow, then the rest of the equation becomes simple. In this case, I have got 4 equations because Jack is traveling not only along the x direction, I mean, not only along the del epsilon direction, but Jack is also traveling along the del eta direction, so he has to write that equation. But I'm also measuring the displacement both along the horizontal direction, epsilon direction, and also along the vertical direction. So that's the reason why I end up with the 4 equations in the case of displacements. Now, using these 4 equations, we can actually come up with the concept of the Jacobian matrix, which is going to be extremely useful. But I hope these 4 equations, how we get this chain rule, please pause and ponder on this equation. And yeah, there is an analogical explanation for how we end up with the chain rule for this equation. Hope this is useful. So thank you all for your patience.